quarter of a century in space exploration. That's how much the ISRO had lost as a result of USA's ultimatum to Russia that it must not provide cryogenic engine technology to India. Despite all that, ISRO managed to open up a new chapter in scientific research with the successful launch of GSLV Mark III from the Satish Dhawan Space Center in Sriharikota on June 5, 2017. The debut mission of the GSLV with a locally developed cryogenic engine proved India's capability to the rest of the world. It was after decades of hard work and overcoming numerous obstacles that ISRO had accomplished this. The roadblocks included false espionage case fabricated by Western countries, which viewed India's growth in this field with skepticism. During the Cold War era that followed the World War II, the United States and the Soviet Union competed with each other for military and technological dominance. Space race was a part of that. In the 1960s, the rivalry reached its peak. Both the Soviet Union and the United States were attempting to outdo each other in space by launching large rockets, spacecrafts, and even humans into space. However, Indian space research was still in its infancy at the time. India's ambition was to expand the groundwork laid by the SLV program and launch larger satellites into geostationary orbit. As a newcomer to the field, ISRO was unable to obtain the necessary cryogenic technology. Since developing this technology indigenously would take a long time and will be very expensive, India had decided to purchase the cryogenic engine and its technology through technology transfer. So ISRO decided to approach Japan, the United States, the Soviet Union, and the European Space Agency, who were all experts in this field. However, Japan showed no interest in this proposal. The United States General Dynamics agreed to give the engine and technology to India in 1988, but only at a price of $800 million. It was a huge amount for India at the time. Besides that, if the US government bans transfer of technology at a later stage, India will be forced to pay a huge price for each launch, as ISRO will have to buy their engine each time. A similar amount was quoted by the European Space Agency too. As India's hopes were fading, ISRO started to work on developing its own engine. It was then that Soviet Russia came to India's assistance. They promised to offer India with 2 engines and technology at $200 million. Clearly, this was far better than the American offer. ISRO and the Russian Space Agency, Glavkosmos, signed an agreement on January 18, 1991. India also sent ISRO engineers with expertise in rocket engineering and propulsion technologies to Russia for training. Nambi Narayan was in charge of this group. A year had passed by, and then US raised its protest against the deal. By then, India had proceeded with training sessions, and half the contract value was paid to Russia. The deal, according to the US, violates the Missile Technology Control Regime for the transfer of ballistic missile technology. The United States' point was that India may build intercontinental ballistic missiles using Russian cryogenic engines. In fact, the solid propulsion booster technology used in the PSLV itself was sufficient for India's ballistic missile program. After the US Space Shuttle and the Titan rocket, the PSLV had the world's 3rd largest solid booster. As a result, India didn't need to incorporate more advanced and costly cryogenic technology into its ballistic missiles. We must note that when US's own General Dynamics offered India the same technology 3 years prior, the US had no objection. That was clearly a case of America's double standards. Mikhail Gorbachev, the then USSR chairman, and P.V. Narasimha Rao, the then Indian Prime Minister, strongly opposed this America's observation. However, Soviet Russia was on the edge of collapse, and the new Russian president, Boris Yeltsin, was nothing more than a puppet of the US. George Bush Sr. took advantage of the situation by imposing a 2-year ban on the trade of cryogenic engines and components, and prohibited ISRO and Glavkosmos from entering into new contracts during that time. The ISRO-Glavkosmos deal was led by U.R. Rao, the then chairman of ISRO, In January 1993, Bill Clinton, who was relatively pro-India, was elected as the new President of the United States. U.R. Rao met with the US authorities multiple times during the presidency of Bill Clinton, and eventually the US decided to classify the agreement into individual parts. As a result, the United States okayed the sale of Russian engines to India with no technology transfer. The cryogenic engines were imported to India from Russia under the guidance of Narayan, the cryogenic team's head at that time. Recognizing that diplomatic action alone would not be sufficient to prevent technology transfer, the US took the help of CIA to restrict the flow of raw materials and spare parts to ISRO, as well as to discredit those who participated in the program. They even succeeded to some extent, as evidenced by Narayan's suffering as a result of the ISRO espionage case. Anyway, our Supreme Court ruled that Narayan is not guilty, released him and gave him the compensation he deserved. Despite these obstacles, ISRO scientists continued their research and development of the cryogenic engine. The cryogenic engine-based GSLV Mark III rocket has already powered Chabdrayaan 2 and will power future Mangalyaan missions and the planned manned space mission. Why cryogenic engine? A PSLV rocket's maximum payload is currently only 2% of the total weight of the rocket. The PSLV XL, the most powerful, weighs 320 tons. As a result, the rocket can lift a maximum of 3,800 kg to a range of 2,000 km and 1,200 kg to geotransfer orbit. This is due to the low efficiency of PSLVs, solid and liquid propellants. Carrying more weight to greater altitude needs more power, and that means more fuel. Hence, they must carry extra solid or liquid propellant due to its huge weight. If bigger satellites are to be launched, more efficient engines are necessary. This is where cryogenic technology becomes necessary. When liquid hydrogen and liquid oxygen are combined, huge thrust is produced very effectively. That is cryogenic engine in a nutshell. However, the hydrogen and oxygen, which are gases at room temperature, can only be liquefied at temperatures of -253° and 183° respectively. The study of materials at extremely low temperatures is referred to as cryogenic science. Besides the fact that cryogenics needs specific materials and technology, it is extremely complex to incorporate it into a rocket. For instance, the launch of Chabdrayaan 2 on July 15, 2019 had to be postponed due to a cryogenic stage leak. Otherwise, India would have lost the 1,000 crore rupees that she had spent on the mission and may have resulted in other unforeseeable damages. With the introduction of the cryogenic engine, GSLV was able to carry larger payloads than the conventional solid or liquid propellant-based PSLVs. Countries that possess cryogenic engine technology, such as the United States, have done it after decades of research. In these countries, cryogenic technology is even used in booster rockets. As a result, they can carry higher payloads or travel to larger distance. Though, India has made it to the list of countries with this technology, with GSLV Mark III. A lot more research needs to be done in this field. India will use cryogenic technology to launch Chabdrayaan 3, future Mangalyaan 2 and future manned space missions. The scientists at ISRO have overcome a lot of hardships to transform India into one of the world's few space powers. Let's wish them success in all their future missions. Jai Hind.